All right, chapter 6. So this chapter keeps building on what we've done before. Got some more basics here. Um, so first of all, when we're looking at this chapter, the idea here again is reviewing again gases, liquids, and solids and these intermolecular forces. But now we're going to kind of go a little bit further with this, right? So remember that an intramolecular force, those are the ones that are within the molecule, right? So this is when we're dealing with our ionic bonds and our covalent and polar covalent kinds of bonds. But then remember we had the intermolecular forces, which so far I really just spoke about introducing hydrogen bonding and vanderwaals, right? So we're going to talk a little bit more about that, as well as going over a bit more on gases and the changes of state, right? So before we were already sort of looking at this idea, the differences between solids, liquids, and a gas. And I think that is probably something that you've been aware of for quite some time, even without taking science. So the strict definition, right? So solids, the atoms and molecules are close contact, and they have a regular shape that doesn't have to be regular. It has to have a shape that's regular that can't be changed, right? It doesn't mean that it has to be a cube or anything like that. When it means very regular, it means that the shape of that solid is what that solid is, right? And liquids, of course, in that case, the atoms are able to interact with each other, but we're now free to move at a certain level in that it will take the shape of its container. And then with a gas, here the particles are far apart, right? They move randomly and they fill the container. Okay, so I think that makes sense. But the thing is, now we have to think about what happens as you switch from solid liquid to gas and backwards. When this happens, there's a change that's taking place, not a chemical change, we're taking a physical change. But in order to free up the bonds as you go from solid to gas, right, as you go in that direction, you're going to have to put energy in, right? And if you look at what's happening, so you remember here melting, right, as when you go from solid to liquid, and vaporization is when you go from liquid to gas, and then going the other way around, right? Condensation is when the gas becomes a liquid again, and then freezing is when the liquid becomes a solid, all right? Now, if you're going in this direction, so going from the solid to the gaseous state, you have to put energy in, and there's this plateau. So the melting point, right, or if you look the other way, freezing point. If you go from melting point, what's going to happen is that you're going to increase the energy here, and the temperature is going to remain as it is until it is now all into the liquid state. Then it will be allowed to warm up, and then you're going to put energy in at the boiling point, okay? And then there's going to be a period of time where the boiling temperature is going to stay the same until all of a sudden all the molecules are in the gas phase. Consequently, the other direction, right? So now what's going to happen is that it's going to decrease in energy as you're doing this, okay? So as the gas is cooling, right, it's going to give off energy, right, and so on. And it's going to give off energy as it freezes, all right? So remember that the melting point is the same as the freezing, right? And the vaporization point is the same as the condensation or the dew point, okay? All right, hopefully that makes sense. All right, so energy in versus energy out, okay? And then we have these other two processes where we go directly, we skip over a state. So deposition is when the gas goes directly to a solid, all right? Sometimes that's desublimation. And then sublimation, where the solid goes directly to the gas and you miss the liquid. So remember, when you're forming the bonds, when you're forming bonds, you're going to store energy, right? So the temperature will drop. And when you break bonds, you're going to release energy, and it will feel warmer to the touch, okay? Now, looking at these different types of compounds, all right? As you know, ionic substances, they can form crystals, right? So solids. So, and that's why we're kind of looking at them in terms of compounds. So when you're looking at ionic substances and compounds, what you're having here is some sort of a bond. You can think of it as ionic. What you're having is that the ions are interacting with each other, and the melting point is quite high, okay? But remember, this is based on electrons. And because the electrons are being transferred, they are really good conductors when in water, all right? Because what's going to happen is that the ions will be freed up, all right? And so salt would be a classic example of an ionic substance in this case, all right? I'm just looking to see what I have in my notes. Right. Now, the other thing is that if you've got molecules, so here you've got covalent types of situations, and now you're not having what you have in a compound with the electron transfer. What you're having now is electron sharing. So that's a little bit different, right? So ionic compounds or compounds, those are ionic. They're really high melting points, but great conductors in water, right? So salt. Molecules, on the other hand, now we've got these covalent bonds, all right? Now we have electron sharing. So these electrons are not free to move, right? I mean, they're moving, but they're not transferring from one to the other. Now you have a very low melting point, and these substances don't conduct electricity, right? So one example would be water, all right? Right. Now, when we're looking at these forces between molecules, right? So I know we've spoken about hydrogen bonds and we've spoken about vanderwaals, but let's go through and really look at what we're having, okay? Now, you can have interactions between polar molecules. It's going to be very similar to what I was saying with hydrogen bonding, right? So polar molecules, if you look at these types of molecules, you have this unequal sharing of electrons, all right? So they are polar covalent bonds. And what's happening here is that these little molecules are looking like little magnets, that there's one side that's more negative because it's more electronegative, right? More, remember, they have these different electronegativities. On one side, the electrons are going to be more highly favored than on the other side. And when they're in a solid, they will line up like, like this, like little magnets, and they can make, these solids in this way. In a liquid, they're a little bit more free-flowing, but they're still interacting with the different dipoles, all right? And I know this looks very similar to what I said for hydrogen bonding, and it is indeed very similar, all right? But we don't need to have hydrogen here, all right? So a lot of molecules, they have these unequal sharing of electrons, and they will act like dipoles. So when they interact with each other, they're going to have dipole forces, all right? So we have these dipole forces, and these are between polar molecules, okay? So I wrote down in my notes, opposites attract, and that's pretty much how it goes, right? So remember, these molecules, even though that one side is slightly more negative because the electrons tend to one side more than the other, or one area more than the other, they're still overall electrically neutral, okay? Now, this is different than what we had with an ionic compound, all right? So even though you have a positive and a negative charge, right? So remember, the positively charged ion is the cation, and the negatively charged ion is the anion, right? And they form these beautiful crystals, all right? These are not considered dipoles because what's happening here is that these atoms have different charges, okay? Polar molecules, they're not charged. They're electrically neutral. The atoms in there are not charged, okay? So these ones, they're held together with these ionic bonds, but they're not polar, all right? So hopefully that makes some sense. All right, so these are electrostatic kinds of here I did. So electrostatic forces, okay? All right, now, So in contrast, when you have a dipole-dipole between polar molecules, right, they have different charged, oppositely charged ends, charged in like bunny ear quotation things, because we're not dealing with ions, but we're dealing with a different way or a different expression of their electronegativity, right? So remember chlorine, if you look at the periodic table, it's more further over to the right side, so it has a much more electronegative tendency versus hydrogen, which is on the other side of the periodic table, on the left side. So when you look at the polar molecule, this is an intramolecular polar interaction, okay? But intermolecular forces, now this is the dipole. This is what you're invoking, the intermolecular, that is called the dipole. So the intramolecular bond is the polar covalent, and intermolecular is the dipole. All right. Now, the interesting thing is, right, as we were saying, polar molecules electrically neutral overall, but when you look at how they behave like these little poles. So one side is more positive, the other is more negative, and when they interact within a structure, right, so they're intermolecular forces, the more electronegative side is going to associate with the less electronegative side. So and this is where we have this idea of opposites attract, and it would be the same thing as if you were dealing with, say, a magnet, right? So the negative side of the magnet will be attracted to the positive side on another magnet, and so on. All right. So as I said here, electrically neutral overall, but there's an unequal charge distribution in terms of how those electrons are arranged. Okay. All right. Just see, following through here. Okay, now hydrogen bonds, are they polar? Well, yeah, they are, but they're special because their difference here is stronger than a typical polar interaction, right, or a dipole interaction, right? We have the dipoles, and now we have hydrogen bonds, okay? And this is very specifically when there is a hydrogen bonded to a very electronegative atom. All right, so that's typically nitrogen, oxygen, and sulfur is what I had mostly spoken to you about, because again, I'm a biochemist, so that's usually what I consider. But fluorine is also the other one. All right, fluorine doesn't tend to appear in organic molecules, so I don't really think of it as frequently. But now when we're talking about just pure hydrogen bonds, yes, fluorine is another example. Okay, so the attraction here in terms of, again, the way these sort of molecular magnets arrange is over the hydrogen, all right? So that's why it's given a specific name. It's a hydrogen bond, and it's actually a stronger bond than the typical dipole bond, okay? So I had already mentioned this one earlier in the course, all right? So if you look at my notes, it says some polar molecules, often involving hydrogen to nitrogen, oxygen, sulfur, and fluorine, have such different electronegativities that they manifest themselves in what we call hydrogen bonds. Okay, and this is an even more stable interaction than what we had with the dipole. So this is a more powerful. It's still considered a weak bond, but overall, it's a very, very powerful bond. Okay. Now, the other thing that I had mentioned to you, and we were looking at the idea of what I was saying, vanderwaals forces, all right? So vanderwaals is a type of dispersion force. And remember what we looked at in that regard previously. I showed you the image of the gecko climbing the wall. And the way that works is that there's little hairs on the toes of the gecko. There's this huge surface area in contact with the wall because of that. And all of the molecules that make up the touch points there, they interact with the wall with this thing called dispersion forces, all right? And in this case, we don't have to have a polar molecule, all right? But what's happening? Remember, the electrons are in motion. The electrons aren't frozen in space, okay? So what happens is that the molecules will develop these transient, more positive or more negative electronegative areas simply because of the movement of the electrons. All right, so if you would look at, say, and this is a good example here with this molecule. So here you have, say, a nonpolar molecule, and if the electrons were evenly distributed over this entire molecule constantly, it will look like this. There's no sort of charge at all. Charge meaning change in electronegativity. But on the other hand, the electrons are moving. So what can happen is that we can develop an area that's a little bit more negative and a little bit more positive, and it's temporary because the electrons are moving, but it's interacting with another one of its partner molecules, and it can induce another type of switchover in the electrons in the neighboring molecule. All right, simply by this, and remember, this is transient. It isn't always going to be like that. Like when we're looking at hydrogen bonds and polar molecules, they're always going to be polar, right? Hydrogen bonds, of course, they're a type of dipole example here, but a very specific one, all right? But it's always going to have this. But when we're talking about dispersion forces, these are transient, okay? But overall, right, overall over the entire surface, they're quite powerful, enough to have this gecko climb its wall. And these types of dispersion forces exist in all molecules, okay? So remember, these dispersion forces don't require it to be a polar molecule, but it's resulting simply from the movement of those electrons, okay? The more electrons that a molecule has, the more of these dispersion forces you can get, okay? If you think about it that way, okay? So remember, those electrons are moving. They're not just, you know, sitting there. They're in their orbitals and they're moving around super fast, okay? So now, collectively, right, all of these interactions, these dipole interactions are called these dispersion forces, all right? And vanderwaals is one of those types of forces. And sometimes the term dispersion is lost to the term vanderwaals. So you'll see this kind of thing, all right? So now when you look at all of these types of interactions you can have dipole-dipole, and London dispersion are also included in the idea of vanderwaals in a way, okay? So it gets kind of fuzzy when you look at it that way. So how would you look at it? Well, think of dipole-dipole, that's when you have polar molecules, and when you have hydrogen bonding, it's also polar, but it's involving hydrogen, okay? And then these dispersion forces, okay, those are going to be able to exist within any kind of molecule as long as the electrons are moving, okay? That's probably the best way to think of it at this point. Okay, so vanderwaals, as I mentioned, can often serve as a very broad definition that's going to include the dipole-dipole, dispersion, and hydrogen bonding, but it's typically used to describe dispersion forces individually, okay? And sometimes it's called London dispersion forces, and that's what we'll do in this course, all right? So when we're talking about vanderwaals, we are referring to the dispersion forces, all right? I just know that if you go and look at this online, it can get a little confusing, but for our course, remember, we have dipole interactions between polar molecules, hydrogen bonding interactions. Those are between polar molecules involving hydrogen. They're much stronger than the typical polar interaction. And then we have the dispersion forces, all right? Okay, so hopefully that will help you. Now, another example, remember I said these dispersion forces will exist between any kinds of molecules. And yes, here we've got these proteins, you've got endorphins and morphine. They interact with the receptors largely by many of these dispersion forces. Okay, there are obviously other interactions as well. But all of these interactions, hydrogen bonding, dipole bonding, and dispersion, they're all going to be working together when we have these molecules and they're interacting with other molecules, all right? Now, the thing that is also must be kept in mind, right? So ionic interactions, and ions exist, right? I had mentioned that, you know, we ingest salt and it's broken down into sodium and chloride. Now, those ions, they have a charge and they will interact with polar molecules. Okay, so we have a situation where we can have an ion and it can interact with a dipole, right? So a dipole has a slightly positive side and a slightly negative side, whereas say you've got sodium here. This is clearly an ion, right? But it has a positive charge. So when it interacts with a polar molecule, the positive end will be repelled away from this positive charge and it will interact with the side that's slightly negative, right? And I had sort of mentioned that's how water is such a good solvent for salts because it is polar. So over here, if it was chloride, the chloride, which is negative, will be sitting over here on the more positive side of the dipole. Okay, so this would be how a dipole or a hydrogen bonded molecule will interact with an ion. But now remember, right, this is we can have a situation where we can have an ion-induced dipole. So say you have a molecule here, and we have as a nonpolar molecule, it's oxygen, right? We're sharing these electrons equally. But remember, the electrons are moving, and we can have a situation where we have a dispersion force, right? And if you have something that's very positive, so if you have a positive ion, what will happen is that the electrons or the molecule, the oxygen molecule, which was normally even over it, will become aware of this ion and it will have an induced dipole now. So the electrons will be will arrange themselves so that the positive will try to stay away from the negative. So it sort of repel those electrons over here and induce it to be more negative, right? Just because there's electrons available on this ion. I know it has a positive charge, but the electrons are moving around and it can induce a dipole in the other molecule. So that's called an induced or ion-induced dipole, okay? So now if you look at my notes, it say ions can induce a polarity in a nonpolar covalent molecule. And then on the other hand, they're attracted to the partial charges of polar molecules, okay? All right, so hopefully that makes a bit of sense to you. Now, in terms of solutions, right? So remember we have our solution, right, as a homogeneous mixture of two or more substances, right? It's not a compound, it is a mixture. Now, what we have in here then is the substance that is dispersed in there is called the solute, and the solvent is the thing that's doing the dissolving, all right? All right. Now, the thing to remember here, now we add to this. So far, we've just been talking about water, which is polar. And then I was talking about how well it dissolves salt because there's charges on there. But you might have heard this phrase before, like dissolves like, right? So say you're dealing with something that's nonpolar, right? So oil, right? You're probably most familiar with this with salad dressing. If you've got an oil in your salad dressing, it's not going to mix with the water because the oil is nonpolar and the water is polar. And this is where this comes from. So in order to dissolve something that is nonpolar, you need to have a solvent that is nonpolar, okay? So you need to have some sort of an oil or some other solvent that is nonpolar. And this comes back to this idea of the green chemistry where we're trying to not use as many of these solvents because they can be quite toxic and not good for the environment. One of those reasons is because they just don't dissolve in water, all right? So because they don't, they're trying to develop other ways of doing the chemistry with them, all right? But in general, what to know is that if you have a polar substance and you want to dissolve it, you need a polar solvent. And if you have a nonpolar solute and you want to dissolve it, you need a nonpolar solvent. All right. So hopefully that makes some sense there. All righty. Now, so as I said, nonpolar substances would tend to dissolve things that are nonpolar. But remember, the ionic substances, like I said, dissolve really well in water because of those ion-dipole interactions. But large molecules can also dissolve in water because if you're looking at your dispersion forces, so we go back over here, right? So we're thinking about this idea of these resulting hotspots. So now say you're in a polar environment, and these molecules, these larger molecules that are made up of many, many, many atoms, those electrons can have this induced polarity and also be able to dissolve in water. And that a classic example there would be a protein or DNA. These molecules are huge, but they have the ability, because they have some regions that are a bit polar, they have some that are not polar, they've got some that have the dispersion forces. So these large molecules can still orient around this so that they can dissolve in water, these very large molecules, all right? So the dipoles of the solvent can then orient around these local charges within a very large molecule and help it to dissolve, all right? Now, going back to how we learned about all this, and this comes with gases again, all right? So we talked about, you know, the change of state from solid liquid to gas. And as you know, a lot of what was done was worked out looking at gases, and a lot of our understanding of these forces that I just talked about was also worked out with gases. And so there's this theory that was developed on how molecules interact with each other, called the kinetic molecular theory, and it was based on gases. All right, so the postulates here, and these should make some sense to you if you think about it. So the particles of a gas are in rapid constant motion. Yes, because they're free to take whatever shape of their container they want. Now the particles of the gas are tiny compared to the distances between them, right? So if you take a gas and fill up a huge space, they'll take up whatever volume is present. All right, so the particles themselves can be very small compared to that distance. And because they fill up the entire container, the particles themselves don't interact very well, right? And when they do hit each other or the sides of their container, it's considered a perfectly elastic collision. So whatever angle they come in at, they're going to go out at, right? And temperature, the way the air feels, the temperature of that. What that is a measurement of the movement of those particles. Okay, it's the particles bouncing on the sides of the thermometer that's causing that exchange of heat that is then explained as temperature. All right, so the temperature of the air is due to the movement of the gas molecules in that air. All right. Now, with this understanding of gases, there was a certain number of laws that was developed, all right? And if you look at this, the first one is quite intuitive based upon what we know, right? At a constant temperature, the volume of a gas is going to be inversely proportional to its pressure. So if you put that gas under pressure, its volume is going to decrease. So as the pressure increases, the volume is going to decrease. And conversely, as the pressure decreases, the volume will increase, right? And a really good way to think about that is just thinking about blowing up a balloon, right? So as you have this balloon that's blown up and you push on it, right, to give it less space, what's going to happen is the pressure is going to go up. All right. And if you look at this, this is how a lot of engines work, right? So you put a gas under pressure, and it's going to increase the force. All right, so here, the under constant temperature, the volume is inversely proportional to the pressure. All right, and that's called Boyle's law. And so therefore, if you have a gas, the pressure times the volume is going to equal some sort of a constant. All right, and this is where you can get this P1 V1 equals P2 V2, because if you change the pressure, you can figure out the volume. As long as you have one side constant, you can figure out the other variable. All right. So P1V1 equals P2V2, and that is what can be used for Boyle's law. Now the next one was Charles' law, and now we're looking at temperature and pressure, right? So if you now have a constant pressure, the volume of the gas is going to be directly proportional to the temperature, okay? So as it warms up, now remember, these particles are going to be hitting the sides of the container even more because you've given them energy by applying heat, okay? And the pressure is going to go up as that happens, okay? So in this case, it's called directly proportional, all right? So that's Charles' law, all right? So this is when you have V1 over T1 is equal to V2 over T2, all right? Now here, the temperature has to be measured in Kelvin, all right? So this is what we're dealing with here, or in centigrade, okay? And if you have a constant pressure and you lower the temperature, the volume is going to decrease, and that's sort of shown here. So here you put liquid nitrogen on this balloon, so you're cooling the air inside, even though it's got a certain amount of pressure, the volume that it occupies is going to decrease. And then as it warms up again, it will fill the balloon again, all right? So that's the idea here. Now, going back to the way they worked out all of these ideas using gases, right? So we go back to our stoichiometry, and they knew that if they did, combine gases, they're going to get products, right? And going back to Avogadro, right? Now we're talking same temperature and pressure, right? So if you have an equal volume of gas, therefore there must be the same number of molecules in that volume of gas, right? And that helped. So if you have a certain equal volume, so you have to have a certain number of molecules, right, in there that's going to produce that. And that's when you combine that with Gay-Lussac's law, that they're going in whole number ratios, right, that together helped understand, this idea of stoichiometry and what these moles were, right? So Avogadro's hypothesis, again, when measured at the same temperature and pressure, equal volumes of gases have to have the same number of molecules, right? And then at a fixed temperature and pressure, then the volume of that gas has to be directly proportional to the amount of gas there, all right? So if you have a certain number of molecules, the same number of molecules at standard temperature and pressure, it's always going to occupy 22.4 liters, all right? Because then we have the same number, okay? So you could work out how many moles, if you know that 3 moles is going to fit in 30 liters at whatever temperature and pressure you're at, you can then figure out proportionally how many moles 2 moles would occupy at how many liters that would be. Or if you have 45 liters, how many moles will that be? Because this has to be proportional. Okay, and then again, Gay-Lussac's law. We know that when we combine these substances, they're only going to mix at whole number ratios, all right? Because as we learned before, you can't make more than you started with, all right? So when all the measurements are made at the same temperature and pressure, the volumes of these reactants and products would always be in whole number ratios. So together, that would be the stoichiometry, and based upon Avogadro's work, we know that that would be a certain number of molecules. So that would be what we now call a mole, all right? So all of these together can work, because when we're talking about the pressure and the volume of these gases, we're talking about a certain number of molecules. So we were able then to, or the scientists looking at this were able to combine all of these to develop a constant. So the combined gas law just looked at the pressures and the volumes and the temperatures, okay? It's funny because Mendeleev actually came up with this. He was able to put everything together, just like he did with the periodic table, right? He's able to synthesize a bunch of ideas and put them together, but he realized that the constant here would be the constant here. And then you can then put that together with the number of moles. So if you add in the number of moles, then you're always going to get this certain constant. So PV over NT would always, PV over NT would always equal a certain constant called R, right? You don't need to learn the constant for this course, but it helps you appreciate that you can do this for any gas. So now this is now called the ideal gas law because you're combining Boyle's, Charles Avogadro's, along with Gay-Lussac's observations, and lo and behold, we were able to get a theory that will fit for all of this. All right. So really, what you do is you go and you practice practice using this equation. All right. And so you can think about what we did in class and how we did that. All right. So I think I did an example. Yeah, I did example 6.7 from your textbook, so you can sort of look at this and see how this actually works. Okay. Now remember, this is just to reiterate what temperature is. So remember, temperature is a measurement of the average kinetic energy of the gas molecules that are in a container. All right. And it's because of how frequently and how hard they're hitting the side of the container. So that's the kinetic energy is being measured when you're looking at temperature. Okay. Whereas if you think back to an earlier chapter, we talked about heat, and heat is the measurement or the flow of energy from one place to another. Whereas temperature is at the actual movement of the molecules and the kinetic energy that they impart. Okay. All right. All right. Now, the important thing to remember here when we're talking about this part of green chemistry is that the idea of supercritical fluids, and I showed you kind of the videos here, but the thing is that the ideal gas law, it works best under sort of normal conditions. Now, if all of a sudden you have extremes in temperatures or extremes in pressure, or extremes in temperature, extremes in pressure, what's happening now is that you're forcing the molecules, right? So really, really low temperatures or really, really high pressures. What you're doing is that you're forcing the molecules in that gas to come close enough to interact with each other. All right. So this comes back to this idea back here. This is why this is in this chapter. I know it might not seem like that at first, but when we're talking about these dispersion forces, right? So usually when you're talking about a gas, the molecules in that gas are so far apart that they're not really interacting with each other. But if all of a sudden you're cooling these things down so low that the molecular motion is going down, or you're pushing them together under high pressure, all of a sudden the electrons can interact somehow between these molecules and you're getting these dispersion forces, all right? So all of a sudden a gas can behave as a liquid, and this is really important. So if you have over a critical temperature and pressure, a substance can behave as a liquid and a gas, all right? So a supercritical fluid, all right, can dissolve like a liquid, but it will flow like a gas. All right. So it can also work at very high temperatures if you really increase the pressure. So this is when you have these extremes. Okay. And in terms of green chemistry, now all of a sudden you can have something that's normally a gas like carbon dioxide or water vapor. All right. And it can now behave differently and then be used as a solvent. Okay, and eliminate the idea of using toxic organic solvents, because now they'd be able to somehow dissolve or provide a platform for a non-polar organic substance to reside in and have a reaction take place. All right, I know that seems really weird, but it doesn't really work when it comes to the ideal gas laws. All right, so the ideal gas law works for when gases are behaving nicely, all right? But when you're causing the molecules to interact with each other, they will do different things, all right? So this is the idea here. So what should you know? Well, supercritical fluids result when gases are under extremes of temperature and pressure, and they can behave differently under those situations because at that point, the electrons or the molecules are forced to interact in a way that they normally don't interact. All right, so hopefully that makes a bit of sense. And that's why the point of showing the video, so that you could see all of a sudden they would crawl out of their containers and things like that they normally wouldn't do as a liquid. So they would do weird things. But that's sort of the point of that. And hopefully that makes some sense. And in terms of what to know, well, try to at least know the basics that I put in the study guide, and hopefully that has increased your understanding about solids, liquids, gases, and intermolecular forces.